In this video, I want to give you a sense of the relationship between kinetic energy and momentum. Both are related to mass and velocity, right? Although this information won't be essential, it is nevertheless useful to help you just grapple with these ideas, perhaps at a slightly deeper level. Now, momentum is always conserved in any kind of collision. That's before, during, or after the event. Right straight through a collision, momentum is conserved. Not so much with kinetic energy. But in any case, I want to look at the kinetic energy and momentum of two objects, object 1 and 2, that are going to have the same kinetic energy. So the kinetic energy is the same, but the masses are different. Mass 1 is greater than mass 2. And what we're going to do is, while they're in motion, we're going to stop them. So F is the stopping force applied in the opposite of the motion. And so the same force is applied to each mass opposite its direction until it's brought to rest. All right, so since the kinetic energies are the same and the masses are different, the speeds are different as well, aren't they? But nevertheless, since the kinetic energy has to be reduced to zero, it requires work, because work is delta K. So the work is the same for both. If the force is the same, then what does that mean about D1 and D2? The stopping distance. Okay, well, since the kinetic energies are the same, and that's Fd, the force is constant, and then Fd1 is equal to Fd2, or D1 is equal to D2. Same delta K, same F, same D for both of them. All right, you with me so far? Well, let's keep going. How do the momenta compare? Now, K is 1/2 mv squared, and that's 1/2 mv times v, which is 1/2 rho. mv is momentum times v. Now, it's also 1/2 mv squared times m over m. Didn't change anything, did it? So I'm going to keep that stuff in the numerator. I'm going to do it like this. M times m is m squared. V squared is v squared. And this quantity is mv times mv, which is rho times rho, which is rho squared. So 1/2 rho squared over m. Then 1/2 rho 1 squared over 2m over m1. So this applied to mass of object 1, I should say just object 1, is the same as that ratio for object 2. But we know that the masses are different, namely that m1 is bigger than m2. So if m1 is bigger than m2, and these two things are the same, in other words, the ratios are the same, then what must be true about this? Well, this one must be bigger if this is bigger. Okay, so the momenta are not the same, even though the kinetic energy is the same. So now let's look at the stopping time. The time, T1 compared to T2. We know the distances are the same. You might be able to have an intuition about this already. The change in momentum 1 is F delta T. The change in momentum 2 is F delta T as well. So 1 and 2 is subscripts. Now, the momentum of object 1, the greater mass, was greater than object 2, even though their kinetic energies were the same. So F delta T1 is greater than F delta T2. Therefore, if the forces are the same, and this is bigger than this, what does that say? Object 1 requires a larger impulse. Since F is constant, the time for the applied force for object 1 is greater than for number 2. So the times have to be different, because the first one does have a larger product, F delta T. So to summarize this, the net force acts on both masses for the same amount of distance. So the distance that the net force acted, which is just that applied force F, is the same. But the net force must act on the larger mass for a greater amount of time, even though the distance is the same. All right? Because it's moving slower. Moving slower, you're going to do the same distance. You're going to apply that force for a larger time. So here's the fundamental distinction between momentum and kinetic energy. The change in momentum, if you have a change in momentum, it's due to the impulse, defined by J equals F delta T. The time over which the net force acts. By contrast, however, the change in kinetic energy is a result of the work done on the object. And work is F delta D. So you're seeing it right here, the fundamental difference. That's a consequence of the distance over which the net force acts. So here we see this mystery of nature. And both are dependent on mass and velocity. But fundamentally, momentum is related to how long a time the force acts, whereas the kinetic energy or the work is related to how far the force acts, the distance over which the net force acts. So let me conclude this video by giving you a practical example of what I was just talking about with the difference between kinetic energy and momentum. So would you rather catch a 1 kilogram catfish moving at 4 meters per second or a 0.2 kilogram guppy moving at 20 meters per second? Now 20 meters per second is really fast. But hey, either way, you've got really good reflexes and you can do it. So you can take your pick, which one you'd rather catch. You got to catch one of them. Isn't this a fun idea? Let's consider the momentum first of all, and for the catfish, and it's mv, which is 1 times 4, which is 4 kilogram meters per second. The impulse to bring the rest is exactly equal to the change in momentum, which is going to be then negative 4 kilogram meters per second, which is 4 Newton seconds for the units for impulse. Now for the guppy, we have a fifth of a kilogram, but 20 meters per second. That's the same momentum. Therefore, it's the same impulse to bring it to rest. The same force times time will bring that smaller guppy that's whipping at you really fast to rest. Same impulse, force times time. Now, kinetic energy, 1/2 mv squared. And the work to bring that to rest. Because kinetic energy and work are related, so the work done is going to be equal to the change in kinetic energy. Catfish, 1/2 mv squared, the kinetic energy, is 8 joules. So the work to bring it to rest, the work is going to be negative, meaning the force is in the opposite direction, minus 8 joules. For the guppy, 1/2 m times 20 squared is not 8, it's 40. So the work to bring the rest in this case is minus 40 joules. That's a huge difference, isn't it? 5 times as much work to bring the guppy to rest than the catfish. So how can we make sense of this? Well, for a given force F, that's what we have in this problem. The retarding force is F. So it takes the same amount of time to bring the two fish to rest. So that's what we had for impulse. Same amount of time, same force. But to bring the guppy to rest is going to require 5 times as much work. There it is. It's 40 joules, minus 40 joules. So if the force is the same, that means the distance is going to have to be 5 times as much in order to make the work 5 times as much. Kind of makes sense when you consider how fast it's moving. And that guppy's coming at you real fast. By the time your hand makes contact with it, you're moving your hand with the motion, with a certain force. The acceleration has to be much greater than in the case of the catfish because it's moving so fast. So to bring it to rest in the same amount of time, you have to have 5 times the acceleration. Doesn't mean the force is bigger because the mass is only a fifth, okay? So it's still the same force, but your arm moves 5 times the distance that it would if it was then the catfish. Okay, hopefully not too confused yet. If you wanted your arm to move the same distance as the catfish, you would have to apply 5 times as much force. So you would, from the time the guppy hits your hand, you have to put a huge force on it, but it's moving so fast, it means you're stopping it real fast. Now the impulse would still be the same, as we've already seen. But in that case, the time would only be a fifth of the original time. It'd just be a boom, and it'd be over with. Okay, kind of hard to make the sound effect to show you what I'm talking about, but your hand, by the time it contact your hand, just it'd be over with. Whereas before, it took 5 times as much. It took 5 times the time. Where the distance is much greater. Okay, so that hopefully spells out for you to some extent how these differences arise: work and impulse. So that's about enough physics fun for this video. Remember, if you're whipping dead fish into a lake off of a pier, let go.